Yeah, thank you, Sören.
Thanks.
And hello, Felix.
Hi, Markus. Good to have you here. And thanks for joining us in this dSPACE Learning Connection.
Thanks for the invitation. And today we want to talk about 3 challenges when testing AUTOSAR in a model-based development process. Basically, the inspiration came from questions we hear a lot from customers. And so we decided to structure our agenda along these questions, right?
Exactly, because that's what we hear from customers. Which architecture level should I test on? What's a good size for a test? Especially in AUTOSAR, which also defines various levels. So this is the first question that I get. And we will answer that today.
Yeah, and the second question is, how can we efficiently handle the different AUTOSAR interface in the different AUTOSAR communication types during mill-till-pill testing? Of course, we need to talk to them. We need to access the signals, access the variables. So this is the second topic which we will discuss and also have a demo about.
Yeah, because of course, AUTOSAR is very specific about what those interfaces look like. And then the third thing that we get is there are all those different test methods. Which ones should I use? What do they mean? So those are the 3 things we want to answer today.
Yeah, and I think especially during the third one, we will take a bit of inspiration from the ISO 26262 standard, because when we talk about some best practices, some test methodologies, then of course the ISO standard gives us a nice hint on what we probably should take care of.
Yeah, I think we always refer to ISO 26262 because in the end, it is really a good compilation of best practices regarding development and testing and makes life really easier if you follow it.
Yeah, absolutely. And let's maybe get started with a short fun observation from a LinkedIn poll, which our colleague Nabil Khoury has recently done, which gave us some insights into the adoption level of AUTOSAR. And basically, the first question was about the interface types between AUTOSAR and non-AUTOSAR. And there we learned from the community that around 50% of the automotive software is developed according to AUTOSAR. At least, well, that's what people answered on LinkedIn, so it's not fully representative, but it gives us a hint about the adoption rate. And maybe even the more interesting one was the second question: how is AUTOSAR software developed? And there, the feedback was that around 80% of the AUTOSAR software is developed in a model-based way, and this is especially true for the application layer above the RTE, right? Basic software, and probably not that much, but
yeah, and that doesn't surprise me at all, because I can't imagine anyone having fun and enjoying writing RTE codes by hand, but we will see that in a moment.
Yeah, exactly. And I think we already used some AUTOSAR expressions which we did not introduce, and we probably will not introduce all of them because we want to focus on the testing part. And there was a webinar which we already did, BTC and dSPACE together, back in June, which was focusing more about the development process. And Felix, I think this webinar is still available as a recording, right?
Absolutely. It's available on the dSPACE website, so you will find it there, and contains various hints on how to model and how to make effective use of AUTOSAR in your modeling processes.
Okay, so we're not going to repeat everything here. So just go to the Learning Center on the dSPACE website, and you can access this information about the development process. And yeah, let's jump into the first question, right? And the first question is, on which level should we test? So what do you think, Felix, about the general levels we have here on an AUTOSAR architecture?
Yeah, we've said it before. It's kind of the most frequent question we get, and AUTOSAR already has quite a rigid and solid foundation when talking about different levels. So we have a software architecture that consists of software components. So the SWC, software components, common term in AUTOSAR. The technical term is atomic software component. And if you have several of those connected in a special way, then you have a software component composition, which typically makes up a complete user function from the automotive point of view. And then further down inside each software component, you also get an internal behavior which usually consists of runnables, and those runnables communicate via ideally interrunnable variables. So the interrunnable variable is one important type in AUTOSAR. And also there are RTE events. RTE is the runtime environment. So this is the AUTOSAR runtime that triggers the runnables. So there's a special method in AUTOSAR also to decide when things start. And now the question really is, which of those levels, the architecture, the internal behavior, the software component, the runnable, where should I test? What's the optimal solution for most efficient workflow? And I think looking into ISO, maybe Markus will help.
I mean, we can look at this from different perspectives. I mean, if we look in the ISO 26262 standard, there are basically two levels. Also from a test perspective, there's a unit level, there's the integration level, but the world in general is more complex than this. So if we go to the model-based world, we can have models, we can have state charts, we can have subsystems, we can, for more complex systems, we can work with reference models or library for better management. So in the end, it's not just these two levels, it's a multi-layer architecture with has sometimes 10, 20 layers of models and subsystems within. And then if we look at customer projects that are not AUTOSAR, there we really see a zoo of different expressions that are not standardized at all. So sometimes they say, okay, we have a feature and the feature has multiple modules and the module has multiple functions and the function has multiple units. So this is really a little bit random, which is okay. We just have to make sure that everyone, at least in one project, speaks the same language. And then if we turn to the AUTOSAR standard, the world is a little bit more standardized because we have the compositions that you just mentioned, Felix, but also compositions can have a multi-layer architecture, right? So I can have like subsystems in Simulink, I can have multiple compositions within each other. And then of course I have the atomic software components, I have the runnables, and then Felix, can I have stuff which is smaller than a runnable?
It's certainly possible. And I mean, if I look at those slides, it's already clear. You said we don't know in non-AUTOSAR what a module is. And I think that's one of the huge benefits of AUTOSAR. Then the term is defined. Everybody knows what the atomic software component is and what the runnable is. The standard defines that. And then if you imagine a model with a runnable, then of course, as we see on this slide, also there can be subsystems inside, and you would also use subsystems to make your model readable, but you probably wouldn't want to test each subsystem. So yeah, definitely there will be levels below the runnable. And well, in my opinion, honestly, well, sometimes people also have this and it's used, but also runnable, in my opinion, would make a good unit. But I think to answer this question, it makes sense first to ask Markus, from a testing point of view, what makes a unit a unit? So what should a unit be and what should it not be? I think that will help in also drilling down to the question, what is a unit in AUTOSAR?
I think that brings us closer to probably exclude some of these things. And I just made a little bullet point list here. So for me, what's important when I talk about units, a unit should have a black box behavior. A unit should have a behavior which I can test and then I can ship it. And the behavior of this unit is not influenced from outside. So one very important aspect of this black box behavior is for me the single point of entry, right? I want to call it and then execute it, right? So if you, for instance, have a subsystem where your function calls going in, it can't be unit because the behavior, the scheduling is influenced from outside. So that's important. And then, well, since the ISO tells us to do unit tests, probably another precondition for calling something unit is you need to be able to test it. And that has two aspects for me. First of all, being able to test it means I need to be able to isolate the element and run it on the different execution levels like model and code. But also the ISO standard asks for restricted size and complexity. And this is clearly something, I mean, Felix, we talked about the AUTOSAR standard standardizing things, but it does not standardize the size and the granularity, right? So if I have 100
That's
runnables and each one has one input, or if I have one runnable and it has 100 inputs, this is totally my own choice.
Yeah, that's the decision of the software architect in the end. And of course, that's then designed for testing, where you cut your runnables in a way that they can be tested.
Yeah. So we have to find the sweet spot there, right? If we make them too small and just have one line of code in each runnable, it's probably not efficient. But if we make them too big and have 500 inputs on a runnable, then also it will be hard to really test it. And then the last point here on this list is you got to have requirements. I mean, it's pretty obvious that we need to do requirements-based testing on the software unit level. This is extremely clear in the ISO standard. So if I don't have requirements on a certain level, I probably won't be able to call it a unit. And yeah, I think
how would I know what to test without requirements? Yeah, it's just not possible.
Well, and how would I know what to implement? So it's a sort of a brain to model process, and so in the end, I think all these bullet points lead us to a conclusion to say the composition and also the software component, they cannot be units because they are not self-contained. They are not black box because they communicate via the RTE. Okay, so if we go back to that slide, the communication in between the runnables, these inter-runnable variables, although it seems like it's something local inside of the software component, it will go via the RTE. The scheduling of the runnables is influenced by the RTE. So this is why the software component cannot be the unit from my point of view, because it has these external dependencies.
On the RTE events, exactly.
So, and I think you teased this already a little bit, that probably the runnable is one of the most obvious choices for being a unit, and maybe smaller functions if I decide to have them. But if we want to be really, really strict and interpret the AUTOSAR standard in a very strict way, we could also argue that smaller functions inside of a runnable are not allowed because they often introduce a global visible scope. And normally the idea of AUTOSAR is to make these runnables reusable in a way that they have sort of a protected namespace, and you avoid naming conflicts, because besides these RTE calls, you don't have any globally visible objects inside of a runnable. So maybe these smaller functions could be seen as a violation of AUTOSAR, although we see it a lot in projects, but from a theoretical side, it could be a problem.
Exactly. I think that's the important point. If you are pure AUTOSAR, and then runnable is a perfect choice. It's self-contained and you have everything. But if you use smaller functions inside, then of course you can also test these. If your overall runnable is too huge, then test the smaller functions and call them a unit. It's also possible. Yeah.
So especially for our demo later, let's agree that we want to focus on the runnable level for our unit test.
Yeah.
And yeah, I think that already brings us to the second question, right?
It does, definitely. And then that would be, what would I want actually to test? Is it the model? Is it the code?
Yeah,
I think it should be both, right?
Before we talk about how to talk to the AUTOSAR interfaces, we have to talk about where do we want to talk with them. Do we want to do it on the model and the code level? And I think this is a very important discussion, because we see that there are definitely some projects that used to do head code. Now they do model-based. They use the same testing methods where they only test the code. And I think this is acceptable from safety, from an ISO 26262 perspective, because the code is what goes into production. But from a workflow perspective, it's pretty inefficient, because if I focus my testing,
lose out on a lot of the options of model-based development if you just focus on the code. You can make your life a lot easier. I also think so. I agree, if you use the model.
Yeah, because it would, if you don't simulate on the model level, you use Simulink like PowerPoint. You just draw boxes and lines. And
exactly.
If you find a bug in testing the code, you cannot fix it in the code because it would break the link, right? So you have to go back to the model, and this is a very difficult and error-prone workflow. And but only testing the model is also not a good idea because the code is what goes into production. So we should test the code. And so, as you said, we should test on both levels, which in the end means it sounds like more work, but it can be very efficient if we work with test solutions that can run test cases in both worlds, right? So it's definitely not a good idea to sort of work with two different test environments for these two levels. And to discuss a little bit more how we should talk to these AUTOSAR elements, let's discuss a little bit how they look, right?
Yeah, because we were discussing actually how to talk to the interfaces and how to identify the interfaces and so on. And for that, I think it really makes sense to get a feeling for the problems, because looking at this example of AUTOSAR sender receiver communication, which is a fairly simple kind of communication actually in AUTOSAR, then you see that in the generated code, like in the applications of the component 1 on the left-hand side, there is no write to a variable outside of the application because the variable is a local variable, but instead you call a function. And also to read from another runnable, you will also call a function. So in the generated code and in the production code, you have the functions, and you need to know about what they look like. You need to map them to a signal in the model, to something that your function handles that is actually something in the application domain that you're building, like the motor control valve or whatever. And so you need to simulate that, you need to connect. And for simulation, we generate in target link an implementation that's outside of the production code, so you can simulate and test that even in the model. And I think that's a very helpful part. So the question now is, how can I map all those things together? Because there are different levels that help separating things, but that also make it a little bit more complex at first glance, at least, to manage those things.
Yeah, so I think the big message here from the testing side for us is also a lot of people often say, well, if you need any stubbing code for the testing, the stubbing code should be generated by the test tool. And of course, in general, we are able to generate stub code. But if we work together here with a code generator, let the code generator do the job. I mean, that's what it's built for. And the code generator target link has also all the information about the RTE macros and the AUTOSAR interfaces. So it's definitely the safest and most efficient solution to just let the code generator generate this code. And then Felix hopefully separate the production code from this stubbing code RTE implementations, right?
Yeah, and I think lots of what we just said would become clear if we basically, with the knowledge about how this looks like in code, we just take a look now at how that would look like in the model, because then lots of the things already lose all their threatening power, because it's really simple in the model typically.
Yeah, before we do this, I want to share one more thing, because here we talked about the most common way of communicating, which is the sender-receiver communication. Yeah, let's have a quick look before we jump to the model to how client-server works. And because client-server is a function call, and the question is, okay, how in the code it's a function call, how can I model this in the on the model level? And I think the great news is that for client-server function calls, which just have a set and get behavior, so either they only receive data or they send data, target link allows us to model this with standard in and out ports, right?
Yeah, so those are getter setter, some external service that I just want to read. And we can just use that in many, many cases as a normal port. There isn't more to it than a data that comes in.
Yeah, and this is really cool because it means my model architecture can be independent from the AUTOSAR architecture. So as a Simulink guy, I don't have to care about, is this sender receiver, is this client server? I just say it's an input for me. I don't care how it's done in the code. And then something people get confused about. I mean, this is an input, right? It's a get function, but the argument is arg out. So that's a question we get a lot.
Yeah. So
and I think the easy answer is that the direction of these arguments, they are just defined by AUTOSAR from the perspective of the server. So if
Exactly.
I'm the client, I call the server, I want to get some information from the server. It's going to be an input for me, for the client, but for the server, it's an output, and therefore it's called arc-out. That's AUTOSAR has decided that for this direction, it's always the point of view of the server. So that's, if we remember this, it's pretty easy.
If you look at the pattern, then of course, for the simple case, if there's just one value to be gotten, then it could theoretically also be just a return value of the RTE call. But I mean, in reality, it's from the standard, it's not restricted to just one argument, and we will see that briefly. And if once you get several arguments in, then it definitely makes sense to use this return value by parameter in order to make this just canonical. So that's a good thing. Okay.
But if we want to call the server and we want to provide data and wait for an answer, especially for synchronous client-server calls, probably we have to model it in a different way, right?
Yeah, like there would be, I mean, the left two ones would be things like you call a global time and you ask them for the current time. That's a typical get operation from this AUTOSAR server. This could be something like, please convert one unit to another unit or something like that, because then that's something where you need to provide an input and expect an output from the server call. And one thing that's bidirectional, typical application. And for that, it is typically modeled as a subsystem, because you put a value in and you get another value out. And then the question really is, how do I get the behavior of this server into the model?
Right, because the server in this example is typically an external function, right? So it's not part of my SUT, but somehow, of course, it needs to do something for my unit test. So I think targeting gives me two different modeling styles for deciding how I want to treat these servers.
Yeah, I mean, as you said, I think it bears mentioning that the typical server operation in AUTOSAR is, in most cases, even in a different software component. Yeah, it's always a separate runnable, and so in the model, it's something I use. And so we have basically two modeling styles that are listed down here. So the first one is I can just go ahead and include a subsystem that models the behavior. This will not become part of the production code, but it's available for simulation in MIL, in ZIL, and in PIL. Or the other option on the right-hand side stub is that you actually just put in reads and writes from a typically data store. That's what we usually recommend. And by that, you can basically model arbitrary things on the outside of the simulating subsystems. You can stimulate them with arbitrary test data and have a lot more flexibility in testing in the end. But you cannot just run the simulation without the test tool and expect proper results. So there's kind of a trade-off, but both options are possible and recommended depending on your use case.
So especially in the second case where I don't have the behavior of the server, I can basically create some, I think it's called signal injection, right, in TargetLink, where I can inject the signal here, and then I can treat the answer, the return value from the server as an input. And then, of course, the big question is how can I explain to my test tool that these little blocks in the middle of the model should become inputs? And in an ideal world, the test tool should be able to just find them automatically, right? So I don't want to explain in general, and this is what we'll see in the demo. I don't want to explain my test tool how the interface looks. This should be auto-extracted.
Yeah, I think what this boils down to, what we just said, is that if I call a server operation from my software component, then the call to the server operation is part of the interface that this unit under test has. But since it's somewhere deep inside the model, or in manual code, it would be hidden deep down inside the code somewhere, it's not so obviously visible, and it could be a pain to find that without the right tools.
Yeah, exactly. You're right. And this probably brings us to our first part of the demo, where we want to show a little bit some examples about these aspects of AUTOSAR-based testing, the scheduling of the runnables, sender receiver, client server, and calibrations. So let's maybe start in the dSPACE targeting data dictionary, where we have already imported an AUTOSAR XML file. And this is, yeah, probably, Felix, I would say the central place, right, where I can find all my AUTOSAR elements.
Exactly. So we keep the AUTOSAR information and target link in the targeting data dictionary, and the model will then reference those elements. And you can see the seed heat control, that's a software component. And the software component has ports that communicate to the outside that can be referenced. It has inter-runnable variables, and we've seen them in the sketch before in PowerPoint, where the runnables inside this one component communicate. And there are 3 runnables that we see. And then we see also 3 different trigger events, all seem to be on a 10 millisecond level, that actually trigger the runnables. And this is what AUTOSAR prescribes, and that's what we need to find in the model. And then let's look at how this looks in the model.
Yeah, by the way, we see that somebody was very lazy naming these runnables, so I apologize for Nabil because he was yeah. And let's as you said, let's check how this looks in the model. And I think it's important to mention that we can actually generate the model from this here, right? So somehow there's an AUTOSAR generate frame model feature. So usually the model is not created manually, the model is auto-generated, and then we can put the behavior in.
Also, the AUTOSAR information will be read from AUTOSAR XML files into the data dictionary, and it can be diffed, etc., and updated, and the generated model can be updated automatically, etc. So there's a lot of automation in handling these in the workflow, but that has also been shown by Sebastian and Nabil.
Yeah. So, well, here we have this level corresponds to the software component, right? We have 3 inputs, 2 outputs. We picked this example of a seat heating because everybody knows how it works, right? You have a button and you press it multiple times to have the different sort of temperatures, intensities that you want to have. And we have 2 inputs. We check if the power is on, we check if the seat is occupied, and then we have the heating request, so pretty easy. And
this level, the subsystem maps to the software component composition.
Yeah.
In what we've seen before.
Exactly. And then here we can see our 3 runnables, right?
Oh, then I was wrong. Then it doesn't. Then it's the single software component. Sorry about that. It's a single software component in this case. Going back to the architecture.
Probably this level is the composition, and then this level is the software component, and then going in, I have my runnables. Okay.
Exactly.
And I have the scheduling.
Sorry about this,
right? So this is.
Yes, because then now what we have is that the 3 subsystems will become runnables, and the runnables will become the production code that goes into production. And this level that we see here is generated by target link, but sorted out during the AUTOSAR export process. And it contains an explicit modeling of the scheduler that generates the timing events. So in a real ECU, that would be part of the RTE, and it would be done by configuring the AUTOSAR ECU. And we don't have that here, so we model it, and we have the freedom to model it. And the best place to do that usually is directly inside the target link subsystem that contains the individual runnables.
Yeah, absolutely. So the scheduling should be inside of the target link subsystem, because then target link generates code for it, and we can use the scheduling on the mil, sil, and pil levels. And then inside of the runnables, we have the interfaces. So here, for instance, this is a sender receiver interface. We can see it here. We can see all the nice metadata which target link shows us for scaling, min, max values, etc. We have an output, which is an interrunnable variable. We have another runnable, the runnable 2, where one input is actually a client server call, where we check the heating request. And yeah, should we generate some code to show how quickly how this looks in the production code? Okay, so this is basically our production code. We have runnable A, And we see that all the behavior of this runnable has been generated in one single line of code, which actually shows how nicely Target Link is able to optimize the code and really sort of inline all these RTE macros in the operations instead of putting them to a lot of local variables and stuff. So I think this is really a nice example of code optimization that usually you can get from code generator like Target Link. If you write hand code, you might write it differently for better readability. But
I never failed to be amazed, even though I've been doing that for many years. Just I wouldn't want to write all these tedious RT, IRV, write, run, AA, connectivity, blah, 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 blah by hand. It's just not necessary. It's so much easier just asking a code generator to generate all this stuff.
Okay, for the second runnable, of course, we have a bit more logic. We have some state variables, and here we can see the client server call. And all these calls are implemented by Target Link in the background as RTE stubbing code, which basically means we can now see how to create a test project for that, right?
Yeah.
And of course, I could now try to go in the model and put some test frame here and connect this, etc. But we think this is a bad idea for two reasons. First of all, I don't want to have any manual effort for setting up the test project. And I also want to have a test project which is independent from the system under test. So we believe that the test tool should not influence the system under test. So actually, this is just dummy stuff here. We could delete it. So when we need a test frame, we will generate it on from scratch in the background, and we never introduce any additional blocks in this model, which also means we can test easily on the different levels. So what we will see is when we have a test project, we will have one test project which allows us to test either on the top level, meaning software component, or to test individual runnables. So let's quickly see how that looks. If I create a test project for this model, then we can have a quick look on how the different AUTOSAR interfaces are represented from a test point of view. So this is probably the model. This is probably the init script. So what embedded tester is doing now, we trigger another code generation to make sure that we have a consistency between the current code and current model state. And then once this is done, you can see that we've identified the model structure, software component, and the three runnables. We could deselect levels if we don't want to test them independently, but I'll keep all of them. We identify the calibrations, which, by the way, we didn't show in the model, but we have some calibrations which have also an RTE call in the code. So
and are also interface variables, therefore.
Yeah. And then we can decide how we want to deal with code coverage. And there you see that we have one file for the runnables and that we have one file for some glue code. So we could deselect this to say we don't want to measure code coverage for this because it's not part of the production code. And that's basically it. So without any manual effort, we have created an empty test project, which has all the information about the system under test. So if I go here on the left side to one of the hierarchy levels and I look at the interface, you can see on the top level, I have 3 inputs, 3 calibrations, 2 outputs for each one. Target Link has told us fully automatically how the resolution min-max values look like. And for the smaller runnables, you can see that we have the smaller interface. We can jump to the model with a hyperlink if we want to see where a certain block is located. So this is one of the calibrations. So that's what an empty test project looks like with all the data ready.
And I think it doesn't matter now whether that was client server or calibrations or sender receiver. So embedded tester just sees the interface and has it here. And exactly. This is the model level, right? So this is from a model point of view.
Yeah, you're right. The first 2 inputs here are sender receiver. The third input is client server. But basically, as a test engineer, I don't really have to care, right? It's an input. I can provide values. And you're right. This is the model level. So these are the names from the model. And I could also switch to the code level. So here you can see how the corresponding variables are called on the code level. So I can sort of switch the namespace if I want to see something different.
And the tester knows the mapping.
Exactly. So this is very important. So if, for instance, if we have a calibration that we want to have different calibrations per test case, embedded tester knows how to talk to a calibration on the model level. Maybe the value is in the MATLAB workspace, maybe it's in the data dictionary. And then on the code level, of course, it's in the RTE stubbing code, and the tool knows where to find it. So we don't have any effort to create the test harness manually.
Okay.
So then, before we start creating test cases, maybe we talk a little bit about the different test methods, because that's our question 3 for today. Which are the test methods which should be applied? And yeah, we could look at it at from a point of view, best practices, model-based design, right? Which this slide tries to show. Yeah,
and there it's really, you want to test the code. We've been there. We want to test the model. And in model-based design, in order to most efficiently use that, it really makes sense to separate those into those 2 red boxes. So you have one part where you do functional testing of the model. That's where your requirements test if the model implements the requirements. And if you have that, then you can take a second step to just verify that the code matches the model behavior. So I really like the notion that the model now has become an executable specification against which you can then do a second fully automated test step. And so the way you do this is that you test the model against the requirements. That's functional testing. Once you are green here, then you can test the generated code versus the behavior of the model. That's a mil-zil-pil comparison, and that's what we call back-to-back test. And once you get that, then you know both is true, both is correct, it does what it should do. And the result is that our customers tend to say, we don't find coding errors anymore. Now we find modeling errors, which is, of course, a lot easier.
Yeah, absolutely. So, and this is also pretty much directly mappable to the ISO 26262 standard, which recommends different methods for the unit testing, like requirements-based testing, like interface tests, back-to-back test. And the ISO explicitly tells us that we can do the testing on the model level, followed by a back-to-back test between model and code. And the standard also tells us about some of the completeness criteria we should have for our tests, especially the structural coverage, because if in our unit test we have only 50% of the lines of code executed, then probably we cannot claim that this test is complete. And
that would also work for models, of course. So also models can be tested for coverage.
So, right, and I think these are exactly the points that we want to jump to in our demo to talk a bit how to approach these test methods for AUTOSAR models efficiently. So we want to talk a bit about requirements-based testing, model coverage, code coverage, and then the back-to-back test. So remember, we have a seat heating model here. So the first thing I would want to do for requirements-based testing is import some requirements. Typically, I want to do this directly from my requirements database. We think it's pretty error-prone to use some exchange formats like Excel or so, because then you never get the right version. So here I'm connecting actually to IBM DOS Next Generation. I have one project in this database, so it's directly talking to the server. For the more technical interested viewers, it's using this OSLC standard for client-server-based communication between DOS and clients. And here I have one module which is called seat heating. So these are my requirements for the seat heating. And now if I import them, I have a list of requirements, and for each requirement, I have my requirement description. I have a link where I can jump to my original data source in the browser. So this is where the requirements is managed in DOS. And now let's maybe create a test case for this request. So if you press the button multiple times, it should toggle the temperature stages. And basically, I have 4 requirements which talk about this request, and I can create, to save some time, 1 test case for all of them. And I know that my runnable 2 implements actually this test. So I'll just create a test case for runnable 2. You see my interface is pretty small. I have the button, I have the temperature stage, which I want to be on. And now I just need to press the button. And I can do this, for instance, with a signal generator, because here it's going to be much faster. So I have a square signal, and now you can see that my button will get pressed 4 times. And I know that in the beginning, I'm in the temperature stage 0. And then when the button is pressed once, I go to my highest temperature, then I go to the temperature stage 2, 1, and then back to 0. So that's how it works. And now I can execute my test on model or code level, maybe even on both, to see if this requirement has been correctly implemented. And now I mentioned that you don't have to manually create the test harness with you don't have to take care how these signals, how the calibrations get connected to the model. So this is now created in the background on model and code level. And now we see here in the table, or well, we could even plot this. We can see that here on top, these are the button presses, and here on the bottom, you can see how these temperature stages change. So we can say that this requirement has been, or these requirements, because we have, you see down here, they are shown, we have 4 of them for the button press. They are now successfully tested on this level for the runnable 2, where this test case is connected.
And I noticed that in here, it didn't really matter anymore that there was AUTOSAR involved, because that's all been taken care of when you imported the interface, right?
Exactly. So the test engineer who is just creating test cases from requirements and running them, he doesn't need to have any specific AUTOSAR knowledge. And if I want to debug something, maybe imagine that this test case is failed, I can create a debug environment just for this test case. And remember, I'm running it not on the full model, I'm running it on this smaller runnable 2. And now actually we are generating an isolated sandbox, which looks like this. So it's the test case, including signals and calibrations. And you see that we have generated a brand new target link model where only this runnable 2 has been isolated for debugging purposes. So that makes it really easy to just focus on smaller parts of the model for debugging, maybe even share the debugging environment with colleagues or customers. Yeah, this is something that target links allows us really to do, to generate these kind of models.
That's really neat, and I think that really helps. And that also underlines what we said before, that if you have smaller units, of course, then those models will be smaller, faster to work with, and you will have a chance of finding out why a value at the input doesn't come out the way you want it at the output.
Yeah, so let's still stay on this runnable 2, because now we have a test case. So now I started actually the model coverage measurement. So this will allow us to see how good our model coverage is for this model. And here in this HTML report, we can now see that, well, on the top level, it's pretty bad, actually, because we only have test cases for this one subsystem. But if we go to the detailed report, well, we have 100% condition coverage, and we have 40% decision coverage on the model level. And the code coverage is something we measure in the background. And there on the code, you can see we have 100% statement, 100% decision, etc. And this is also shown in the annotated source code. So you see here, everything which is green has been covered. You see here's one condition which has not yet been false. So this is probably something we want to cover. Yeah, that's how the code coverage works like. And then let's quickly talk about the back-to-back testing. So let's still stay on the unit runnable 2. We could, everything we show we could do on the integration level as well. So for the runnable 2, you can see that we have some condition coverage missing. So I can generate some additional test cases for getting full condition coverage. And this is now one feature of the tool where we generate tests automatically, which will guarantee us 100% coverage, or they will prove that something is unreachable. But here you can see we generated one additional test, obviously, which brings us now to 100% condition coverage. And now I can basically run a back-to-back test, right? And what we want to do is we want to compare mil against sil. Maybe we'll do this just on this level. And then you will see that 100% is passed. So we have one test case where mil and sil do the same thing. And I can also view this, I can plot this, but you can see that this is the mil, this is the sil. They both do the exact same thing for all the steps. So now my back-to-back test is also green.
Cool. And how do I know that the tool, when evaluating the tests, really worked and didn't make any mistakes?
Yeah, I think you have to trust the tool.
Okay.
And either you do it because you just believe me and you trust my word, but if you want to be a bit more professional, you can also ask the ISO 26262 standard how to create this trust or how to create this confidence. And if we look at the ISO standard, we see that if you want to trust a tool, you need to earn that trust by performing a tool qualification. If you don't do the tool qualification, it means you cannot have any trust in the tool. And then the standard tells us a little bit how to get to this tool qualification, right? And there are like 4 different options presented.
Yeah, the standard asks us first to also ask how much do I need to trust the tool, and then that's the TCL here, the tool confidence level, and 3 is the highest. So it says I need to have very high trust in the tool, and then to gain that, I could use one of those methods here. But if I want to go to a high ASIL, it would be 1C or 1D. And yeah. I mean, of course, validation of the software tool, that's hard, especially if I'm not the vendor. So as a customer, that's tough. And I will definitely not develop a embedded tester in compliance with safety standard. I don't develop embedded tester, or I just want to use it. So what can we do? What do you do?
So basically the most common methods are the 1B and the 1C. So evaluation of the tool development process and the validation of a software tool with a qualification kit, a validation suite. And then of course the question is, who's going to do the work, and are the tool vendors helping, right? Because yes. Obviously yeah, there are a lot of degrees of freedom. And what can the tool provider now do to make your life easier as a user? And option 1 is nothing. So obviously you have tools where the tool provider doesn't provide you anything for ISO tool qualification, and you can do it on your own from scratch. And this is a lot of work. You will have a lot of discussions with auditors to argue for completeness. And this is an option which you see for a lot of tools, but it's of course also an option which you see for most of the in-house tools which have been developed internally at your company, probably by people who are no longer there, or which are poorly documented. So especially for in-house tools, this tool qualification topic is usually a nightmare. The option 2 is you can have a tool provider which provides you or sells you, often people take money for this stuff, a qualification kit, which is sort of a starting point for you to perform your tool qualification. And you have to do some stuff on top. You have to run the things. You have to argue for completeness. You have to deal with possible errors. So this is option 2, which is always already a little bit better because at least you have a starting point, right?
Yeah, but it's still lots of work.
Then we see tool providers that go one step further, and they go to some authorities and ask them to certify the qualification kit, which is slightly better than option 2, at least a little bit. You probably still have the same amount of work on the customer side, but at least you have some additional confidence that the content of the qualification kit makes sense and is in line with the standard because somebody has already approved it. And then, of course, option 4 you have a tool which is by itself certified, which means all this effort for tool qualification has been performed on the tool vendor side. And if you meet some preconditions in the project regarding workflow, regarding obviously regarding versions, right? So if you take Target Link and you try to install it on a Windows XP, which is not supported with current versions, then probably you cannot benefit from the certificate. But this option 4 is definitely the one which has the lowest amount of work on the customer side. I would even say it pretty much eliminates the tool qualification effort inside of the project. And this is the approach which we have taken as BTC for embedded platform and embedded tester. You see that on the right side. And also dSPACE is working with a TÜV Süd, a very famous and trustworthy organization. And they have issued these 2 certificates for ISO 262 compliance to show that both tools can be used even for safety critical projects up to ISO D.
Exactly. So we've chosen route 4 because I think that's the only reasonable way to provide a tool on the market.
Okay, so that already brings us to the conclusion before we jump to the Q&A session. So we discussed 3 questions we hear a lot from customers. The first one is which level to test on.
And we came to a conclusion. We recommend to test on the runnable level. If you have functions inside the runnable, that's also fine. That can be done. But the recommendation would be a runnable.
Yeah, and the second question is how to manage the AUTOSAR interface for testing. And I think the best conclusion was don't get a tool which does it for you. Then you don't have to think about how to connect test data to different types of interfaces. You don't have to think about that client server is different from sender receiver. Try to let the tool handle all that for you.
I'd go so far as to say AUTOSAR, in my opinion, was never meant to be handled manually. It was meant to be handled by proper tooling. And the complexity in AUTOSAR makes that possible. So use a tool when working with AUTOSAR.
Absolutely. And I can also say that of course, we do a lot of customization for customers that have project-specific needs, but these project-specific needs are always smaller in AUTOSAR projects compared to non-AUTOSAR projects, because it's just much easier to predict what people are doing if they rely on such a standard.
Exactly.
Okay, and question 3, which test methods should be used? There we took some inspiration from the ISO standard, right?
Yeah, and I think ISO just lists it all. As I said, it's best practices and all of them should be followed. I think they are all reasonable and necessary together with back-to-back testing that allows to shift most of the testing efforts actually on the model level, which makes handling, especially debugging, a lot easier. So
yeah, absolutely. And probably the mother of all questions at the end of our webinar, will our testing get more difficult or will it get maybe even easier when I use AUTOSAR?
And I think it will be easier. As I've said, lots of stuff can be automated. It's more consistent. So if you use the tools, it's probably in the end easier than doing plain code testing.
Yes, I fully agree. And that brings us to the end of our webinar.
Thank you so much, Markus and Felix, for the nice presentation. And yep.
So thank you very much also, Markus, for being here. And it's been a pleasure as always. And so everybody have a nice day and see you soon, I hope.
Thank you for the invitation. Thank you everyone for watching.
Yeah.
Goodbye.
Bye.
Thank you. Bye.
dSPACE, your partner in simulation and validation.